The next reaction we're going to talk about are called haloform reactions. That is when you take a methyl ketone. So let's draw a methyl ketone. So a methyl ketone is going to have a methyl on there, and then this side right here can be whatever we want it to be. Okay. So I'm just going to put on, clean this up here, like that. You see that carbon that's directly attached is not a methyl ketone. The carbon that carbon is directly attached to the carbonyl, and that carbon is directly attached to the carbonyl. That is the methyl ketone part, because that is a methyl group that's directly attached there. So another way of saying it is that the methyl group has to be a alpha carbon. Okay, so we can see that is our alpha carbon, and that's our alpha carbon, and those two alpha carbons, they're different. Okay, so if we take a methyl ketone and we treat it with halogen under basic conditions, okay, we treat it with those conditions and then do a second reaction where we do a acidic workup. So let's say sulfuric acid, some kind of acidic workup. What's going to happen is that's going to generate, look at this functional group here. We generate a carboxylic acid. That's our product. And then we would have this species right here, X3. Now look at what's happening here. Let's try to bring this all in. To see how we have the alpha carbon right here, or the methyl ketone part? That carbon right here is that carbon right there. And so we should be like, whoa, what's going on here? Carbons are not good leaving groups, but now we are saying that they are. And the reason for this discrepancy, or this apparent discrepancy, is this piece right here, we call that a haloform. Okay. And haloforms have carbon attached to it, or it's made of carbon, but 3 halogens. And so what we've done overall is we have 3 hydrogens here. We've replaced those 3 hydrogens with 3 halogens. And when you can replace those 3 hydrogens with halogens, that carbon atom now becomes a reasonable leaving group. And I'll go through the details a little bit more when we look at the mechanism. Another thing to keep in mind is this X2, or the halogens. You can use chlorine, bromine, and iodine. You can use those 3 halogens to make this transformation take place. Okay, so let's go through the mechanism and go through the details of this and how this all works. So here's our methyl ketone. I'm going to take the 3 hydrogens here and expand them out so we can see them, like so. So the first step in the mechanism here is going to be a proton transfer, because we're going to take our hydroxide here and do a proton transfer. And why can we do a proton transfer? Because remember, alpha hydrogens are acidic. So we're going to generate this species right here. We have our 2 hydrogens still left. We just generated some water from that attack, but we have an anion right there. Okay? And so now, what we can now invoke here is treating that anion right there with the halogen. Let's say we're going to use bromine. Okay, so There's our elemental bromine right there. And we are going to do a SN2 style mechanism here. So we'll go like here, SN2, electron rich. It's going to come, backside, boom, just like that. And what's that? That's going to generate this CH2. We added our bromine, just like that. And there's going to be a bromide anion floating around. Okay? Now what's going to happen is we're going to do these two steps right here, the proton transfer and the SN2, 2 more times. Okay? Do it 2 more times. And so what are we doing? We're going to replace another hydrogen and replace it with a bromine. And then we'll do it a second time. And eventually we will get to this right here, Br3, like that. Now we're still under basic conditions. And so we can have our base now, the hydroxide. We can do a nucleophilic addition step. Like so. So that will give us something that looks like this, a tetrahedral intermediate. Like so. And now we're going to take that tetrahedral intermediate and we're going to collapse it down. So if that collapses down, look at what happens here. That collapses down. And so if we collapse it down, something has to leave, right? And so that process right there, that's called our nucleophile elimination mechanism. And so this right here has become a good leaving group. So that leaves. And that's going to generate what? A carboxylic acid plus our CBr3 minus, like that. Now, what's the next step here? An irreversible proton transfer step. Because you've just generated carbon with a negative charge on it. Not very stable, but stable enough to be a good leaving group, And so what's going to happen? The moment that's formed, it sees a carboxylic acid, and we're going to do that irreversible proton transfer step to generate the carboxylate. And then that generates CBr3. So when you look at all the different types of halogens, we call that the haloform. But since it's bromine, we call that the bromoform. Okay? And one reason why this is irreversible, or the reason why this proton transfer step is irreversible, is because the bromoform, or the haloforms, that guy right there is insoluble. So it crashes out of solution. And so that Le Chatelier's principle says, okay, it's crashing out of solution, so we've got to keep going to replace what we're losing. And so that's a major driving force for this reaction here. And so now we're at this point. We are not to where we need to be yet. And so we have one more step. And what is that last step that we need to take? Well, that's the adding the acid. So that's the second reagent that we're going to add. So we would just simply do a proton transfer by adding some acid. And so we'll just represent that by a hydronium. So we could see, hey, we do ourselves a proton transfer, and we would generate our our carboxylic acid product. And there we go. There's our product. So I want to spend a little bit of time at this step right here. Okay. So making the leaving group leave. And I just want to do a comparison so we can see it. All right, so let's do a comparison to try to understand why this reaction works. Let's draw ourselves a typical methyl ketone right there. Okay. And then I'm going to draw a haloform. And let's look at bromine, Br3. Okay. Now, when we do the nucleophilic addition step, what is that? That's the base that's coming in like that, right? So let's draw that now. So we're going to do our nucleophilic addition step for both of these. Minus OH CH3. I'm going to have to use a different marker. This one's dying on me here. Okay. And then we're going to have the nucleophile elimination step, because that's going to collapse back down, right? Collapse back down, and then that should leave. That's what we're thinking is going to happen. But why does this not leave? Because we generate the methyl anion right there. And if this guy does the nucleophile elimination, we would get this. But this does happen. So let's put a big X right here saying, nope, that can't happen. But this one, yes, it does happen. Why? When we look at that anion right there, very high in energy. It's a negative charge on a carbon, not a very electronegative atom. But when we see a negative charge on this carbon, what's going on here? Well, if we expand it out, okay, what are those bromines doing that the hydrogens are not doing? Well, we know bromines are electronegative. So it's going to suck electron density that is on the carbon towards the bromines. And that induction right there helps to stabilize this anion, stabilizing it enough that it can act as a leaving group. So that is not a good leaving group, cannot happen, but this is an okay leaving group because of those three halogens that are attached. And those three halogens are stabilizing that leaving group. Now, it's very important that we understand that it is a methyl ketone that can work. If I change this methyl ketone and just replace one of those hydrogens with another carbon, the reaction does not work. Let me explain. So we could have ourselves a methyl ketone right here. Okay? And we do our reactions, the two reactions here, and we can generate our carboxylic acid just fine. And we would have our HC, and we'll just do general terms, X3. That works great. But if I replace one of those hydrogens, and let me draw it, I'll expand it out, with a methyl group, okay? So this is not a methyl ketone. This alpha carbon right here only has 2 hydrogens. So if we treat it with the same conditions as above, we are not going to generate a carboxylic acid. What we're going to generate is a species that looks like this. And I'll do general terms, so X for a halogen, X for halogen, CH3. So this carbon right here, even though it has 2 halogens, it's not good enough to leave. It can't. It has to have 3 halogens directly attached to that alpha carbon. So 2 halogens are not enough. You have to have 3. That is why methyl ketones are the ones that you're looking for when you want to do a haloform reaction. It has to be a methyl ketone. Okay?